we will see a problem, example 7.1 from the textbook. The conducting triangular loop shown in the figure carries a current of 10 amperes and find the H, that means the magnetic field intensity, at the point 0, 0, 5. Okay, so first of all you see at the point at 0, 0, 5, due to the side 1 of the loop, okay, you need to find only what is the magnetic field intensity produced at the point 0, 0, 5 due to the side 1. Okay, where is side 1? This is side 1 actually. Side 1 is here. So due to this, how much is the magnetic field intensity at the point 0, 0, 5? So first of all, we need to clearly identify where is the point 0, 0, 5. So the point 0, 0, 5 means x is equal to 0, y equal to 0 and z equal to 5. Okay, so you see here, if I draw it in a different way, we can have like this as the z-axis, and you can see here in the question it is given like this is the x-axis and y-axis. Okay, so please note carefully. So it is like a top view. Okay, it is like a top view. Actually, you can see that the z-axis will be pointing towards you. So the z-axis will be coming towards you actually. So in this case it is coming towards me. So in this case you see in the figure, let's say this is figure 1. So in the figure 1 actually it is coming, the z-axis is coming towards me. So I can view it in a different way also by seeing the side 1 only, because in the question it is asked to find what is the magnetic field intensity due to the side 1 of the loop. So first of all I will draw the side 1. So you see the side 1 is on the x-axis. So this is my x-axis. I will draw the x-axis. This is my x-axis, and I will draw the z-axis because I will view from a different angle. Then I can view the z-axis like this, right? So this is my z-axis. So if I view like this, you can see where is your side 1. The side 1 is on the x-axis. It's clear. The side 1 is on the x-axis. Okay, side 1 is on the x-axis. So this is your side 1. Okay, or it is marked like this, side 1. Okay, this is the side 1. Now you see, I want to find what is the magnetic field intensity at 0, 0, 5. Okay, 0, 0, 5. So we want to find what is the magnetic field intensity at 0, 0, 5. So where will be the y-axis? So we will see the y-axis actually. So where will be the y-axis? This will be your y-axis actually, and the angle between the x-axis and the y-axis is actually it is 90 degrees, you know. So this is your y-axis. So I think you can view it now clearly. So I can draw it, the complete picture, in xy plane. After that I will proceed with the problem. So we will see here, this is your side 1. The side 1 is starting from the origin and it will be ending at the x-axis at some point. Then it is moving in the xy plane. And what about the side 3? The side 3 is coming to the origin, and this is okay. So this is what actual picture, okay, including the x, y and z plane. So you see here, this is the loop, and we want to find where is our point. Our point is like x is equal to 0, y equal to 0 and z equal to 5. So this is what we can redraw. So we can redraw the figure like this. Anyway, we are asked to find only the effect due to the side 1. So this is after redrawing the figure. After redrawing the figure 1. Okay. So I will show only the x-axis now and z-axis. So let us consider like this, and this is my x-axis and this is my z-axis, because we are focusing only on the side 1. If we are focusing on other sides, then we need other axis also. So you see here, this is like the side 1. okay, the side 1, and it is carrying, all the sides are carrying, actually it is 10 ampere current is flowing. It is given that the 10 ampere current is flowing, so everywhere it will be 10 ampere anyway. So we have 10 amperes flowing like this. Now how we can proceed? We know that in a current loop, suppose we have a current loop like this in any direction, whatever. If we have a finite element of which is carrying a current, then in such a situation, suppose this is a finite element which is carrying a current. For example, this is the element which is carrying a current. Let's say this is AB and its direction is given as AL. Now what we will find, if I want to find what is the magnetic field intensity at this point P, that means due to this current element AB, you know that the current is going up, so it will be going inside. So how we can find this? We have already explained in the previous videos. So what we will do, I will join with the lines. You see, I will just extrapolate this line and I will find what is the perpendicular distance from my line to this point. So this should be 90 degrees angle. Okay, and what is this distance? This distance is rho. Then after that, I will join from A to this point and I will join from B to this point, and this angle which is outside the triangle which is shown in this red color, so that is known as alpha 1, and what is inside, that is alpha 2. Okay, then I can get this direction, that means the direction of this rho. For example, this is the direction of rho, a rho. Then the direction of the magnetic field is given as a phi. The direction of the magnetic field, the direction of magnetic field is given as a phi, which is equal to al cross a rho. Okay, so you know what is al and you know what is a rho. In such a case, you can find, this is the general thing for a finite element which is carrying the current. So in this case, you know that we want to find what is the magnetic field intensity at the point 0, 0, 5. Okay, so what is the AL here? So in this case, the current is moving in this direction. So this is the direction of AL and this is the direction of X actually. So it is AX. Okay, and you know, this is my perpendicular distance. Now you see here, this is the perpendicular distance. So my perpendicular distance, you know, this is my rho. So in this case, it is along z axis, so rho is equal to phi, and I know what is the direction of a rho. Now you see it is moving towards az, so it is a rho is equal to az. Okay, now I want to find what are the angles alpha 1 and alpha 2. So you see here, I will join to this point and I will join to this point. Okay, so alpha 1 is the angle outside, so this is my alpha 1, and alpha 2 is the angle inside, and this is my alpha 2. Okay, so I hope it is clear to you. So what is the formula? The general formula for finding the magnetic field intensity is H is equal to I over 4 pi into rho, okay, into cosine of alpha 2 minus cosine of alpha 1 into cosine of alpha 2 minus cosine of alpha 1. So in this case, actually, you know what is the direction also? It is a phi. Okay, so we will see what is the direction now. Okay, so we will see now the direction. Okay, so you see here that you know what is alpha 2 now. So you got what is alpha 2. Sorry for this, I think, yeah, it's okay, I will write it here. So you know a phi is equal to al cross a rho, and al, you see, it is az cross what is a rho? It is nothing but a x, as I have told you. So we will see now what is the cross product. So for that, ax, ay and az. Okay, we can write like this. Now az cross, sorry, az cross ax is nothing but AY. So this is equal to AY. So my direction is A phi, which is nothing but AY. So I got the direction now. Okay. Now we will see what is our rho now. So what is our rho in this case? Okay. What is our rho? Okay. So rho is equal to this height. I have already told you it is equal to phi. Okay. So rho is equal to phi. Now we will see according to the problem. So did I missed anything in the problem? Yes, I missed something. Actually, in the problem it is given this is your origin 0 and this point is nothing but 2. Okay. So in this case, if we are redrawing the figure, this is 0 and this is 2. And here also it is like 0 and 2. Okay. So we got it. So it is 0 and 2. So you can forget about these things. Anyway, this is all the general explanation I have given. Okay, on the right side. So you see here that we have to find what is the cosine of alpha anyway. So we have to find what is alpha 1 and what is alpha 2. So I have told you this is your inside the triangle. What is angle? That is alpha 2. Okay, and outside, for example, it is outside. You see here, this is your alpha 1. Okay. I'm sorry, I have already mentioned the angle. Sorry for this. Alpha 2 is here. Okay, alpha 2 is here, and this is your alpha 1. Okay, so just compare with this picture. It is clear. So here it is alpha 1 and here it is alpha 2. So in this case, anyway, I will mark it again. So you have z axis, you have x axis, okay, and the current carrying loop is here. Okay, now you want to find at 0.005, you have to find the magnetic field intensity at 0.005. So what we will do, we will join here and we will join here, and I told you this is outside, that is alpha 1, and this is inside, that is alpha 2. So in this case, alpha 1 is equal to 90 degrees. Okay, so cosine of alpha 1 anyway, cosine of alpha 1 will be equal to, cosine of alpha 1 is equal to cosine of 90, which is equal to 0. Okay, now what is alpha 2? So we don't want to find alpha 2. Anyway, you know that this distance is equal to phi. Okay, and in the problem it is given that this is equal to 2 and this is the origin. So this distance is equal to 2. Now what is this total distance? You know, this distance will be equal to rho square, the square root of rho square plus rho square plus this distance, that is the 2 square, that means rho square plus this distance, or I can say that it will be equal to phi square plus 2 square, which is equal to square root of 29. So what is cosine of alpha 2? Cosine of alpha 2 is nothing but the adjacent side. Okay, the cosine of alpha 2 is nothing but the adjacent side. What is adjacent side? Adjacent side is already 2 divided by the hypotenuse. The hypotenuse is 29. So we got it. Now we can use the formula h is equal to I over 4 pi into rho into cosine of alpha 2 minus cosine of alpha 1 into a phi. This is equal to I is 10 divided by 4 pi into rho is equal to 5 into cosine of alpha 2. What is cosine of alpha 2? We have already found it. It is equal to 2 over square root of 29 minus 0. Okay, into a phi, and we have already seen what is a phi. A phi is equal to ay. So if you substitute this, you will get the answer as minus 59.1, and the direction is ay. Okay, then milliampere per meter. So the unit of the magnetic field intensity is ampere per meter. Okay, so the unit is ampere per meter. So I hope it is clear. And there is a milli here. Milli means, you know, milli is actually 10 power minus 3. Okay, so this is the answer. I hope the problem is clear to you. Thank you.